write bigger. Okay. So this is just to say what we will do. So today I want to say you what symplectic is, since Alexei claimed he doesn't know. So then I will give two stupid examples. And then I start with explicit embeddings. So they are not high-tech. They are by hand. But they are useful. They give a feeling. And for many problems we study later on, they are already sharp and give precise answers. Okay? Mm-hmm. So this is the program of the first, of the dot one. So then the dot two is tomorrow. So we will look at the J-holomorphic curves. Good, here I am. And then prove kind of Gromov's non-squeezing theorem and also Gromov two-ball theorem. And this will be, to see how things go, very useful. Okay? And then the third lecture is on a problem of you give me one ball and I take k other balls and try to take them as big as I can into the given ball, or in other words, I take k balls of a given size and try to find the smallest ball possible so that they go in. And this problem we will completely solve. Okay? And then from this problem we will kind of see something about fine structure of symplectic rigidity. So Gromov non-squeezing theorem says that there is something rigid in symplectic geometry. And these theorems then will tell us that there is not only a brutal rigid kind of rigidity, but also a kind of fine transition between flexible and rigid, because there are also flexible parts, as we shall see. Okay, so this is the program of the 320 minutes. Well, we'll see. Fine with you, Petya? Good, good. Okay, so this is the program. So now I start with point one, right? Good. So now, since you're all students, I will give you a kind of an idea how to think. Can one see something? Let's check. Yeah, here it's probably even worse. If you are bored, you can learn some Italian here. Good. You cannot read it, right? Okay, I tried to explain what symplectic is. Now, what we all know is that, so in my lectures, it will be almost always in R2N, because it's kind of sufficiently difficult. We will just take balls or convex bodies in R2N and try to embed them in as small as possible, given other domain convex in R2N. So already this is a relatively difficult problem. And the definition of symplectic is given, and everybody knows, and usually it's the end of the class because everybody leaves. So for Nikita and Natalia, I want to give another definition right now, okay? So definition two, definition two goes like this. So first I want to say what a symplectic structure is on R2. So on R2, I take immersed curves, right? I take smooth maps from S1 to the plane, something like this. And they are oriented, the curves are oriented. Okay, and then, or for instance, this, or maybe this, or maybe this. Okay, and to such an immersed curve, I want to associate an oriented area. So, for instance, here, it's just weighted is +1. I mean, it's plus the enclosed area, right? Plus A, it's something like 2, maybe. And here it's maybe something like -2 + 2. So it's 0, right? It's just the oriented area. So here it's something like, well, I don't know. Well, let's not do it. You know what I mean? You just take this curve and decompose it into parts so that you get simply closed curves, and then you have an oriented area, and then you add it up. Okay? So for every such inverse curve, we look at this oriented area, something like area of curve, and this is the oriented enclosed area. Fine. So this is a symplectic structure in the plane. Definition. Good? Oh. So in R2N we do the same, just coordinate-wise, right? So you protest, I will be a little bit not writing, doesn't make much sense, right? So on R2N, well, we just have a curve with components. And then we do the same on every coordinate plane. So this splits like let's say it's already identified with Cn. So then we just say that the area of such a curve is the sum of the area of the components. Fine. So it looks essentially like this. So you have here something like the first R2 and another R2 and another R2. And then you have here a curve. And then you project it to the planes. And then you just take it here, here, and here and add it up. Okay, so this is what I want to say is a symplectic structure on R2N. Fine. Somebody says, fine. Okay, wait. So exercise, the two definitions are the same. There are so many churches in this city that, okay. Okay, so exercise.
What exactly do you mean? Sorry, did you hear me?
So I want to say, so the first definition of symplectic structure was there was given the standard linear constant symplectic form, sum of omega 0 on R2. And now, okay, now we have what? So
what's the meaning of equivalence?
Well, okay, it means that if you have omega 0, you can do these area measurements for every curve by the components and get the same number. And if I give for every curve, I tell you that, then you also know how to measure areas.
Right. And
it's just, I mean, it's just, well, probably Leibniz. You can say Stokes, but it's easier than Stokes. It's just Green-Riemann, probably known by Leibniz, right? Because it's only in R2. So what it means is symplectic structure is a way of assigning to closed curves signed areas. So this was actually the definition known to Lagrange. He of course did not write in symplectic form or anything, but he knew the following. So he knew that he has in a three-body problem in R3 and therefore then R6, if he has a closed curve and he goes with the Hamiltonian flow, well, he called it the development under the solution map, so that then if he does this game, that the value does not change on the time. And if you translate it, he really saw this definition too and the meaning of it. Of course, he didn't know, he did not know in our language about differential forms, but this definition too roughly goes back to Lagrange. And this, of course, also in Arnold's book, right? Mm-hmm. Okay, so this is a symplectic structure. And now exercise for you. How do you generalize these two arbitrary manifolds? So the exercise you did, it goes like this. You take an atlas, and then you do everything in coordinate charts, and you only do it for local curves. And then you say that, well, the transition maps are those local diffeomorphisms in the charts that do not change this, this, right? So this should be, if you have a coordinate change phi, then it should not change these area measurements for local curves in the charts. So then you can lift these two manifolds and you get exactly the same definition as with differential forms for all manifolds. So our definition of manifolds is of course that you have a non-degenerate differential 2 form. A non-degenerate, so, well, you ask Jura, Petya, or Alexei if you don't know what it is. It just means non-degenerate form on every tangent plane, and it should also be closed. And this is equivalent to this atlas business of measuring oriented areas of closed curves. Easy, okay? So this is a way to think about it geometrically, but of course to use and for computations, this is also extremely useful, right? We will use both. Fine. Okay, we go to the so this was this, we did it. So now I should do 2 examples. Yeah. So do the students have seen Hamiltonian mechanics? Alexei, did the students see?
So Felix, I think there are some non-specialists. There are some number theorists in the room. So I.
Really?
Yes.
I see only 2 more people. Okay.
There are
okay. So.
16
okay, then I will be slower. You mean? Okay, I will be more
no,
precise.
no, Felix, it's okay. So I think everybody heard once about Hamiltonian equation. You just write them down.
Okay, let's do so. Of course, it comes from all the way down from Newton, right? Maybe I want to say that. It's kind of important. So historically, the following happened. You have Newton's equation. Newton. And well, it's something like maybe not. So if I take a particle of mass 1 and it moves in a potential, then Newton equation is this. So now this is not a differential equation. So you add velocities, right? So to get a differential equation, so this is say on Rn. Now to get a differential equation, we go to R2n, right? So we take a system.
You mean to get an ordinary differential equation?
Exactly, to get an ordinary differential, to get a vector field.
Yes.
Yes. So there is no m, mass is 1. So we get this. So this is much better because it's now a vector field and now we have a flow. So here we have no flow. Now we have a flow. But we are on R2n. So dimension is doubled, but we don't care, right? So now comes in a way an important step. You observe that the total energy is preserved, right? So you introduce the Hamiltonian function, which may depend on time. And And then you rewrite what we already did, right? Can one still see?
Yes, yes, that's okay, yes.
Okay. So it is now, well, what is it? It's the gradient of this thing by dy at x and y, and minus so it's a skew gradient. It's almost the differential equation if I write xy equal to z in R2n. The differential equation is essentially the gradient, but there is a skew gradient, right? So, sorry, it's not a gradient. I mean, so there is something very strange. There is x becomes, here is a y, and for y there is an x, and there is a minus, right? So it's just a rewrite. But now the key thing of the transition from 1 to 1 prime is that we can geometrize this.
Felix, excuse me, there should be the norm of y power 2.
Yes.
What?
You have y square, the norm of y in
Oh,
the
yeah,
square.
thank you. Thank you. Thank you, Natalia. Maybe. Or Olga.
It was Alexei and then Olga, yes.
Ah, thank you. Okay. Good, good. So you just take the usual energy. If T would be not there, somehow if this would, well, here it is, it could be dependent on T also, but if it does not depend on T, then the vector field is time independent. And in that case, you look at this quantity, which for time independent case is even preserved. And then what is more important for us is that the differential equation now has this form. It's a skew gradient. So what it is actually, it is just I times gradient h at the point xy, right? Okay, well, let me move. Maybe I do move. Well, sorry. Yeah. So you see what happens, it got very geometric. So now this 1 prime reads like this. So we write z equal to xy, and now it reads just z dot is I gradient h at z. And maybe you write j. But it is just the usual I on Cn. On every R2, it's just...
Well, we cannot really see it, but it's just...
sorry.
Something like, yes.
You see that?
No, it's okay.
So this is just I plus I plus I. Right, so now we have a very special vector field. And the Newton equation became now a very special vector field. Okay? So when you are here...
You could make your dots over the I and Z a bit thicker so that, I mean, they got a bit fuzzy. Oh, great.
Okay, so now you're already a bit happier because you have a beautiful vector field. But now comes a very important further step in order to do the geometrification. You rewrite these differential equations by using the symplectic structure, right? So we do something. So we define the vector field xh. It's a vector field on R2n by, so implicitly, by using our symplectic structure, which is maybe more conveniently the differential form definition. Well, maybe there is a T, maybe not, at the point. So what is DH? It's a one form, right? So this means that for every vector at every point here, you have this identity, right? But this was non-degenerate, and it exactly means that this equation determines this vector, right? At every point, this identity tells me that this quantity determines a vector at the place. And this definition will be much better later. So one should check that this definition gives the same as before, but it's easy. So when you do that, you briefly compute and you find it's the thing of before. So we have only rewritten, there was nothing new, but this language will be much better, okay? And the Newton equation from the start is now simply Z dot is this XH at Z, right? So it's very, very short now. Of course, we have introduced notation, but okay, fine. And the flow, it has a flow, and the flow is phi h. So this is the flow, right? The flow of this vector field. Fine. So
we cannot see the flow, but
the flow is here.
better.
So you see, there is already one. So we have done almost nothing. We have just used differential form. But what you see is that this equation here, the last one, makes sense on manifolds. Because all we need is this. So if we have a function, maybe depending on time, on a manifold, this equation, if this thing is a non-degenerate 2 form, defines a vector field, and we can look at the flow. Before, we have written in coordinates, and it was not clear how to generalize. Now, just given a non-degenerate 2 form, closed or not, will come out later whether it's useful, but for the moment not important, defines a vector field and the flow. And I introduced this because these flows are symplectic. Okay? Good. So maybe one thing I want to say is that if you do that only on cotangent bundles, here we are. So let's restrict to the case of cotangent bundles, phase spaces, right? R2n is a special case, but many symplectic manifolds would be more general. And on cotangent bundles, we take the same form as on R2n. It's called dqdp, but when you take a little patch in the base manifold, over it, it's just the same as what you would do for R2n, just the same. So now I want to give a few reasons why this new formalism is much better than the previous ones, okay? So one reason, so what happens? So on cotangent bundles. So you can do the, well, let's assume something like it would be R2n and you would have Newton, right? You can do Newton. Well, then you don't even have a vector field, but you have a differential equation. So then you can, of course, do the Lagrangian formalisms. I did not recall it, but maybe you remember. It's more general. And what we have done is the Hamiltonian formalism. And what happens is they are more general. And so in which sense they are more general? Let's look at the invariance group. Let's look at those diffeomorphisms that keep the structure, I'm not very precise, but that keep the structure of the differential equation invariant, right? So here, it would mean that you still have x double dot equals something. And what happens is when you, for instance, look at the circle and just a pendulum in gravitational field, here the invariance group is the isomorphism group of the base manifold. So it's just the isomorphism group of the base manifold. And this is horribly small. And you see, you want a big invariance group because you want to find good coordinates so that the specific equation of a problem becomes easy, right? So here it is, what is it? It's exactly the diffeomorphism group of the base. Which is much bigger. But here it's much, much bigger. It's the symplectomorphism group of everything. So I will explain in 5 minutes that this inclusion is enormous. This is much, much bigger. So this was actually the main motivation in the time of Jacobi to do the Hamiltonian and symplectic formalism, because the invariance group is much, much bigger. And then many equations that could not be solved, like the geodesic flow on an ellipsoid, or in the three-body problem, certain systems could now be solved. Okay? So again, this is not, with this you can essentially only solve explicitly extremely simple systems. So with this you can do many things, but with this you can do much, much, much more. I have no time to give examples, but you go to Arnold's book, right? It's really kind of, historically, this was the main point why they looked at it. And well, I just tell you, so Moser, for instance, did the following. So he looked at the restricted three-body problem, and then he did a very strange coordinate transformation. So he looked at, just tell you as an information. So he looked at R something like 4, and then he had coordinates QP, because he looked at this as T star R2, and then he changed the three-body problem as follows. He did QP goes to PQ, right? You change places with momenta and vice versa. Maybe minus, doesn't matter. So this looks totally crazy from the point of view of Lagrange, to change places with momenta. But what Moser observed is that if you do that, then the restricted three-body problem essentially becomes the Kepler problem. So it becomes much easier, right? Good. So this is only historical, but for us, the key point is that we have now a geometry, right? We have a physical situation, but now we look at it as a geometry because we have this symplectic form, omega, and its invariance group, and then we work as a geometry, and sometimes you can go back to dynamics and say something. Okay. So, what do I want to say? Okay, I very briefly want to look at the maps. So we will look at symplectic embeddings, and one motivation is that we want to understand, right, this is the invariance group. If you have a geometry, Felix Klein says you shouldn't study the objects in the geometry, but you should study the automorphisms, I mean the symmetries of that geometry, and in some sense it's much more important. And here in symplectic, this insight of Klein is actually extremely nicely illustrated, because even historically, things do not start from the geometry, but from the automorphisms, namely the Hamiltonian automorphisms coming from dynamical systems of three-body problem and so on. So what do we have here? Our heroes are the symplectic methods. So something like the symplectic of M omega. So what are they? They are all the diffeomorphisms that preserve the symplectic form, right? And herein we have the Hamiltonian ones. So
Not visible at the moment. Can you tilt it upwards a bit, a bit less. Yeah, like this, right? Great.
Okay. So what did we discuss? What we are interested in are somehow symplectic mappings. I mean, in this dynamical system is usually really diffeomorphisms. We will just look at embeddings because it's easier. So now here is a subgroup. This subgroup is usually much smaller. But this is from dynamics. You start from dynamics, the flow maps are all here in. Maybe no, I don't say that. But let me prove this. So why is a Hamiltonian mapping symplectic? That's very easy. So let's see. We just have a Hamiltonian time t map, right? Phi h t, and I should prove that this is omega for given t. Okay. So well, I will just prove that this quantity does not change in time, because for t equal to 0. This is time 0 flow map, so it's identity. So it is omega, and I will just check that this is 0. I must check that this is 0, right? Yeah, but now it's useful to know a bit how one differentiate things with differential forms, and the outcome is that, so up to a coordinate change, this is the V derivative of omega. So this is just something if you had a course on differential forms, maybe you know that. Okay? Yeah, but now we use something else, Cartan formula. So this is every Lie derivative of a form is di plus id. So this is d contraction omega plus I d omega. This is for every differential form like this. Lie derivative of differential form.
Sorry. Maybe you should explain what I means. This
I is contraction.
Yeah.
Okay, so I vector field of this two form. Well, this is a one form. And if I apply it to another vector field, it is by definition omega of yx. You plug it in the first lot. You have to make a convention. Let's take this one. Okay? It's called contraction, and then okay, I'm gonna read it.
Felix, I think it would be better to read it in a larger scale. Yes, this formula because
bigger.
Yes, I think I can see. Me personally, I can see it, but maybe for others it will be better.
Yes, yes. So contraction of, I take a vector field, I have a differential form. So what is this? Well, let's do it for two forms. On a two form, I want to create a one form.
Yeah, right like this, yes.
So I have two vector fields, and this is omega of VU. You just plug in one. You can also do it with 5 forms, with K forms. You create the K minus 1 form. It must be such, right? Lie derivative preserves the type. So we contract and differentiate, and also we differentiate and contract. So down, up, and up, down. And it's just a sum. Fine. Alexei, I always see Jura, but I mean, he knows. Okay. But he very kindly makes a very interested face. Okay, so now when in general, this is not so helpful. But now, since we are symplectic, we have assumed that this is 0, right? It was on R2N, it was automatic, and on manifolds, it's in the definition. We need it at several points, and here we need it the first time. So it's closed. So it's this, right? Okay, so now we can go on. So what is this? Well, it's pullback of d contraction omega. So I want to do, no. So I just go on computing this. So it's, what is it? Let me do it. Let me do it here. Okay, it's only this, right? But what is it? Well, it's d of, and what is, by definition, so what is this? Of omega of x h comma dot. But you see, omega of x h comma dot, by definition, was dh, right? So this is, okay, no place, is d, it is d of d h of. Yeah, but this is 0. dd is always 0, right? Well, well, it's of course a mess, and it's in all the books, but I just wanted to show you that all the super elementary thing that you have learned in Calculus 3, I don't know, here are just used to show that Hamiltonian is a special kind of symplectic. And you can also do it in coordinates, but then it becomes a kind of, don't know, it just comes out, but here things kind of fit. Fine. So what we have proven is that every Hamiltonian mapping for a fixed time defines you a symplectomorphism, right? Fine. Okay, good. So maybe I give one corollary, namely Liouville theorem. So this would, okay, let's do it, corollary. So it means that the Hamiltonian flow preserves the volume in phase space, right? It means the following. You're here in R2n, and you have a certain domain of initial conditions. And then you flow. With every point you go somewhere, and you get something else. And in general, it's extremely hard to see what you get. But Liouville theorem says that one thing you know, the volumes are the same, right? Liouville says that the integral of this domain U of omega to the n, this is just up to a dimension constant, the usual Euclidean volume in R2n, right? I mean omega 0 wedge omega 0. So this is the same as the integral of phi t h of u of omega 0 for every t. Geometrically, it just means that when you flow, the volume in phase space is here R2n, and in general, the symplectic manifold is unchanged. Okay? So the proof is extremely easy. Well, it's on one line. It's simply because, so we prove because phi h t pullback of omega is omega, because it's symplectic, right? Well, and now when you do the coordinate transformation, well, from this in particular, you have that phi ht pullback of omega to the n. You know, pullback commutes with wedge. So this is phi ht pullback of omega to the n. And now, well, and this we know is omega to the n. Because of what we saw before. If you are Hamiltonian, you are symplectic, right? Fine. And now it's just change of variables in integrals. Okay. So you see, of course you know Liebel theorem, but this from the if you do it in the Lagrangian formalism, you cannot see this invariance. You cannot see preservation of volume. But when you have introduced a differential form and formulate the Hamiltonian system in terms of differential form, you can see this a priori invariance. The volume is preserved. Fine. Everything good? Oh, Alexei, did you send around the notes?
Did I say which notes?
The one I sent in email 4 days ago.
Do you mean okay?
Maybe
the book?
Maybe the short text rather.
1 moment. Yes, I think I have received something. I can just check.
Okay, because if somebody wants to read it, he can read it. Mm-hmm.
Yes, of course. Yeah, I will distribute to everybody. So everybody who would like to have a lecture, some lecture notes, please let me know.
Great. Okay, so what we have now seen one big family of examples of symplectic mappings, right? Namely, time t flows of Hamiltonian systems. Okay, so I want to give one other very easy family that puts symplectic in a way in another perspective. So I take a diffeomorphism of Rn. I take psi. Cannot see. Huh?
Yes, it's okay. Now it's okay.
I cannot see anything. Huh? You can see it. So I take a diffeomorphism of Rn, and I will now produce from it a symplectomorphism of R2n. So here I have Q, and I take it to psi of Q. So then this map well, let's call it maybe 5. Can you read it? So this is a symplectomorphism, and it looks a bit stupid, but what it means, you see, it's a fiber map. In the fiber, in the base, you do the same, and then on every cotangent plane, this is cotangent plane, you do a linear map given by differential, and it's unfortunately contravariant, so you have to go back. And this is very useful to know that the whole symplectic thing is actually a functor, a contravariant functor. Everything in diffeomorphism group lifts canonically. And you can also do it on cotangent bundles. Fine.
Mm-hmm.
I mean, the picture is something like this. If you have Q and you have phi, and you go to Q, then you can lift everything. But it goes back. And it's, of course, just a pullback map. Right, so every diffeomorphism down lifts to a symplectomorphism. If this is any diffeo, then this is symplectomorphism. So useful to know. Okay, maybe I give now an exercise. So the exercise is to prove that a very thin band in the plane is symplectomorphic to the whole plane. Exercise. For any epsilon positive, let's do 0 epsilon cross R is symplectomorphic to R2. So it means that I have a thin band and even a half band. And this is the same as all R2. So it's an easy exercise. You can write down an explicit solution. But the point is that you see the volume was infinite, so no a priori obstruction. And in fact, you can do it, right? So good. Okay. Please make it. Okay, so this was the first half. And now we do explicit packings to get a feeling what you can do. Are there questions? Okay, I will clean the blackboard. Okay, the whiteboard. Okay, so now we come to explicit packings. So they are totally by hand, but later we will prove that they are, well, we do not really need it, but later we prove some precise results, and these we construct now will show that these hard results from holomorphic curves actually can be seen. So in symplectic results, very often there is a kind of a difference between what can be seen and what can be proven. Sometimes one can realize it, and sometimes it's totally impossible. So what we are doing now for half an hour or so, is to get a feeling of constructions, and later on to see that the results from holomorphic curves that are sharp for also holomorphic reasons, but that they can be seen. Okay? Fine. So explicit packings. So for the rest of everything, we go to dimension 4. So partly because otherwise one cannot do, and partly if one can do, it's easy, and one would not learn anything else if one would go to higher dimensions. In dimension 2, things are very easy, and in dimension 4, they are already not easy, and in high dimensions, either one cannot do, or it's for the same reason. So I now go to dimension 4, okay? So I consider a very specific problem, a ball packing problem, following. So something like this. I take balls, for instance 5, and I try to embed them in a ball as small as possible. And everything is in R4. Okay, so this is kind of problem I want to discuss. Everything happy? Hello. Okay, so what is ball? I will not use radius. Radius is very stupid in symplectic. We will use pi r squared. It's the area of the projection of the ball onto a symplectic coordinate plane. Okay, so the ball of dimension 4, A, it's always the open ball of well, in R4. Well, we look at the so-called capacity, anyway, of capacity A, which is pi radius squared. And if it would be R6, we would also look at this pi r squared. This is a symplectic quantity because it's area, right? It's area of a cross section. Okay? So something like this. And then we have cross section. Well, all the way around, but shit. And this is A, right? Area of a central cross section.
Felix, excuse me, could you please show us the lower part of the blackboard? Yes. And the right part as well.
It's
yes,
pretty hard.
That's it. So thank you.
Okay, so this we will now study. Okay, so now I fixed the number of balls. Are you done?
Mm-hmm.
So we fixed the number of balls. And then you see, if I can embed two balls of size 5 into one of size 12, I can also do the two 10 balls into the one of size 24. Everything is scale invariant. It's easy to see. You can shrink, map, dilate back. Because dilation commute with symplectic because it's just times a number. Because the symplectic form is nice. dx, dy, right? If you can put the linear scale into. Okay? So I can always, one of the two sides, I can fix the scale. And I will take now in the image the one ball and ask for as big balls as possible that I wish to embed. Okay? So our scaling is, so the problem we want to solve is we want to find pk, and it is the supremum of k times, oops. The Italian hate us now. It's strange. All the Ukrainian people that want to learn Italians are girls. It's very strange, no? Can you read that? So the problem we look at is we fix the one ball and we try to make, given k equal balls, but of course a bit translated, we try to find a symplectic embedding of k balls of a given size into the one ball, right? And we try to make A as big as possible. So the supremum over all A. But I don't take A, I can also say, I take the percentage of the volume I can fill. So I have the target and I try to fill it as much as I can with balls. And then I just take the percentage of volumina, the ratio, right? It's a number in, well, it's certainly positive and certainly less than 1. And for every k, I get a number. Fine. Is the problem clear? This problem I want to solve. Okay? So before we start, I want to compare this problem with two other problems. Namely, if here we would have taken either Euclidean or volume preserving, right? They would be two other problems. So you can also take Euclidean or volume preserving. And then here we would have either Euclidean or volume preserving or symplectic. Okay, so let's see. So maybe you don't know, but it's easy to see that if we would take volume preserving, the answer would always be 1. So you see in dimension 2, it's like when you have water, incompressible media, and you can easily deform things so that they just fill. Or when you think of sand and you play in dimension 3 with sand pieces, kind of easy to believe you can completely fill. And technically, it's just an application of Morse trick. When you know this trick, it's 2 lines. Very easy to see that when you work with volume preserving maps, which are more general than symplectic, as we have seen, right? Because omega to the n is preserved, not, well, here omega wedge omega, and not omega itself. Then the answer is always 1. So it means that if you work about volume preserving mappings, this problem is totally boring. For every k, you get 1, right? So when you work with Euclidean mappings, then this problem is extremely famous and extremely difficult. Well, if the target would be R to n, it's Kepler problem, the densest packing by balls. In dimension 2, the bees know. In dimension 3, Kepler knew. In dimension 8 and 24, Vyazovska did it 4 years ago. And in all other dimensions, it's open problem. But if you don't go into Rn with a kind of an asymptotic density, but into a fixed ball, the problem is even much harder because you have these disgusting boundary constraints. So if you give yourself a fixed ball of dimension 3 or 4, and you want to fully fill it, you want to fill it as efficiently as you can with a given number of equal balls, the problem is in dimension 3, bigger or equal than 3, totally open, besides for 1 or 2 balls. So maybe I make one example. When you look at dimension 2, this problem is solved for less or equal than 22 balls. And for k equal to 10, it's like this. So this is dimension 2, it's a disk. It looks harmless. And the answer is, yeah, it has a symmetry. Maybe I cannot do it. Looks about like this. So I think they touch, but I'm not sure. Well, I probably cannot do it. And then it goes around. Well, sorry, it's a mess. Can you see it? Can you see it? It looks like this. Can you see it? The problem is that some of them do not touch. And you see, I looked at books and papers. I tell you, it's very ugly mathematics. It's linear programming. It's not a beautiful theory. They don't have tools. It's horrible. And the great thing is, symplectic looks a priori even much harder. But we have tools, holomorphic curves. And this is solved in dimension 4. In volume preserving, it's trivial. In Euclidean, it's hopeless and ugly. And in symplectic, we have tools and it's fully known in dimension 4. In dimension 6, it's also quite hopeless and not much is known. Okay? Good. Okay, just for, you see, Euclidean is, of course, maybe I should say that, right? So volume preserving is a special case of symplectic, and symplectic is a special case of Euclidean. So I do not say that symplectic implies Euclidean, but no, the other way around. Right? So when you're symplectic, you're volume preserving. And when you're Euclidean, you're actually, you see, you're orthogonal. And orthogonal mappings are not symplectic, but unitary mappings are symplectic. And well, an orthogonal mapping is up to a, now what do I want to say? So a Euclidean mapping is just a rotation plus a translation, right? So for our purposes, since the domain is anyway rotation invariant, namely a ball, we just speak about translations and they are symplectic. So for the ball packing problem, this inclusion is correct. And of course, here the pk is less or equal than the pk. So the pk Euclidean is less or equal pk symplectic, is less or equal than the pk volume preserving. That is anyway always 1 for all k, right? So these numbers are hopeless, and these we can find in dimension 4. Fine. Is it okay? So we change again. It's getting darker here. Oh, shall I briefly show you something about Kiev? Look how nice it is. Do you see it? No.
Wow.
There is something. It's not the. It's called. Well, Andrew's Church something. It's a bit kitschy. It's from the Tsar time, but there are also other ones. Okay. Good. But you have all been there, I know, in the Soviet time. Okay. Good. So now let's see what we want to prove in the next 2 hours. Theorem. So it started with Kromov in 84. Okay, we'll see. And then there was something by McDuff and Polterovich. In 94. And then it was solved by Viran. But nowadays one can do it much faster, thanks to Taub's theory. It goes much faster. Okay, so I give you now the PKs. Okay, so let's see. So what do I have to write here? Who can say? How much of the volume of a ball I can maximally fill by 1 ball? Okay, over 1. Okay, so the other numbers you cannot guess. I will now give them, and you should maybe copy this list. And then we can, in everything we do, we can kind of discuss what it means. So here it's 1/2, and here it's 3/4, and here it's 1, and here I write it on purpose in a very strange way. 20/25.
So Felix, this is in R4, yes?
This is only in R4.
Yes, okay.
So this list is unknown in any higher dimension. But for a very small case, something is known. I will maybe say. Okay. So this table is called T. Can you learn it by heart? So for later on, you can maybe observe that, well, this is 5 times 2/5 squared. Right? It's 5 times 4 over 25, which is 2 over 5 squared. This is 6 times 2 over 5 squared. This is 7 times 3 over 8 squared. And this is 8 times 6 over 17 squared. Okay, we will use it later. Yeah, okay, good. So now we will start proving this list. Fine. So only part of this can be seen explicitly, and I will now start this explicit construction for realizing the lower bounds of this list. The upper bounds need obstructions, and they will be by holomorphic curves, but sometimes these numbers that are gone can be realized explicitly. Okay, so I will need a lemma. I want to think of a ball in a totally different way. I want to think it of as a triangle cross a square. It will be useful. Okay, so lemma. So the ball is symplectomorphic to a triangle cross a square. And the idea is that the square is boring.
Wait.
I want to.
First, the ball is open.
Everything is open. Everything.
Everything is open, and this is the triangle is in the Q coordinates, and the square is in
exactly.
the P.
So the key thing is that this splitting is not symplectic but Lagrangian. This is the key thing. So the splitting here is Lagrangian. It means that this is Q1, Q2, pi 1. You can also write X and Y. Pi 2. So you may know something similar from action angle coordinates, but then it's a torus and I don't want to do that. I will not discuss it. Okay. So again, so this is in something like R2 of Q, and this is in R2 of P. And the main point is that everything interesting, the size, is in the first part in a triangle, and everything else is gone. So later I will just play two-dimensional games, because I will have something which is maybe a bit more than this, but here I will have always a square, and I will just forget about it. Okay, so let me prove this in little detail. So I will only prove it up to epsilon. I will prove that A minus epsilon embeds, and also by the same method that this embeds into A plus epsilon, but then there is a certain way to go to the limit. But it will not be important for us because we always look at suprema. You can always kill the epsilons anyway. Okay, so let's do that. It's a very elementary construction. So you fix positive epsilon. And then I write down two-dimensional symplectic mappings. And these are just volume-preserving mappings that are, well, also orientation-preserving, right? So I take the 2 ball, which is a disk. And I map it somehow, I map sigma into R2. Okay, so now one should see it. So let's call it X1, Y, XY. So it's a symplectic mapping, right? It will be a little bit confusing later with the QP. So I write now XY. It's for the standard symplectic form dx dy, an RR preserving mapping. and I tell you how I map concentric circles, because this will determine my mapping. One can write something down, but it doesn't really help. So I just tell you how things go. So a small concentric part, here I take here. Wait, the goal is to map it to somewhere here. Here 1, here A, and I start here. Okay, so on this disk it's just a translation. And then a somewhat bigger circle is mapped like this. And then a somewhat bigger circle is mapped like this. But it's a diffeomorphism, not like in the picture. And the bigger circle is mapped like this, and so on. Well, I write now down a property, and it will just be realized from such a thing. So what do I want? So I want that sigma is ARA preserving and has the following property. I want that, okay, let's call here the variable x, y, and here x bar and y bar, for instance. Okay, and I want that x bar of a point. So what do I want? I will tell you. I essentially want that the area of the, I take the area of the blue disk, and I want, if it's 1/5, I want to be on essentially one on the left of 1/5. That's what I want. But it's not quite possible. So I want it up to epsilon. And that's easy. So this is less than pi. Well, you know, I want to know, where does this point go? Well, less than where it is, plus epsilon. This I want for every point in the disk of area A. And this is the A disk. And here is, well, here is maybe A plus epsilon, right? Do you believe that this exists?
Can we see the condition now? Right.
So, well, this is just the way, you see, what is this? What is this? Well, it is
What's
just...
X bar? Anyway, wait a second. X bar is the coordinate?
X bar is this coordinate.
Right.
The bar is the image coordinate. So it's almost obvious that this exists because I have the epsilon. So I just, you see, I just want to say that these circles, so actually this map is unique if I impose that this axis, I just give you a system of curves that are essentially rectangles, but they are a bit smoothened because everything wants to be a symplectomorphism.
Excuse me, could you please recall us what is sigma of xy?
Well, it's the mapping illustrated by the picture.
Okay.
So circles of a given color go to the curve of the given color, and things are arranged in such a way that what I want here is that things are as much to the left as possible. You see, abstractly, I want to take this map. But it doesn't work because it must be nested. But I approach this somehow by saying, okay, almost. And here it's extremely dense. And I just give you such a system of curves that are very, very close to rectangles. And this is extremely small. And then I just have, from then I claim that if I tell you that this segment goes to this segment, then everything is determined actually by the picture, by the area condition. because sigma is area preserving. You see, when you have an infinitesimal band and map it here to this infinitesimal band, everything is determined. You can write down an ODE, but it's obvious, right? It can be anyway, it's true. So such a sigma exists, and all I need is this inequality that says that I can take things very much to the left. And of course, the idea is to completely forget about y. Up to this approximation business in the beginning, the y has gone, right? Okay, so this map is my hero. So now I take the product of this map, which is this defined on the product of two disks of area A, and restrict it to the maximal inscribed ball, which is of course the A ball, right? So now you look at sigma cross sigma, but so this is defined on the polydisk, but you restrict it to the ball, right? Okay, so I claim that the image is essentially contained of the triangle cross the square of before. Okay? Maybe I compute it now. I just check it. Either way one can kind of see it, but let's check it. So what happens for a point in the ball, right? So if I take a point, in the ball, so I want to, you see, it's clear that the y part, so in this Lagrangian splitting, right, the P1, P2, they are now the y1 bar, y2 bar. And they are between 0 and 1 by construction. So I only have to think about the first Lagrangian factor, which was called Q1, Q2. But in the construction, it's called X1 bar, X2 bar. Yeah, it's a little bit.
You should write it down.
Oh, I will write it down. I just made a little mess of with names. First it was QP, and now it's XY. Okay, so.
Excuse me. So do I understand correctly that B4 is a bidisk?
Who?
B4 is a bidisk, or it?
No, it's the ball.
Ball.
But sigma cross sigma is defined on the bidisk. But the bidisk, it looks like this. So the ball I'm interested in is the maximal ball in the bidisk. DA cross DA.
But actually, it's more like diamond than like circle.
Yeah, depending on, this is only we will come to the diamond. We like it so much. Is it okay?
So
the largest ball by my notation that is inscribed here is this one. Okay, so I maybe didn't say, but so Alexei, this is this. Okay, it's a disk with area A.
Yes.
Okay, so let's compute this of sigma cross sigma at such a point. Estimate. Okay, so by construction, what is it? It's x1 bar of the first sigma of x1 y1 plus x2 bar of the second sigma of x2, y2. And now, by this, by the thing before, we can estimate that. So it's less than pi times now the x, the first, plus maybe 2 epsilon. Yeah, but this was in the, this is in the ball, right? So this is less or equal than a. This is exactly a pi r squared. Well, this is less or equal than, this is actually strictly less than a. So what does it mean?
Can you shift it a bit so we?
So it means that here are my x1 square, x2 square coordinates. It means that I'm here, right? But I'm also positive. So I'm in the triangle I want to see. Well, up to 2 epsilon, right? But forget it. It's not important. So you really land where you want, in the triangle, cross the square. But if you work on it for a while, you don't need the computation. You really see it for symmetry reasons. Yeah. You see, the aura condition becomes a linear condition because we did it this way and the y has been kind of cancelled. Okay, so this will be very useful. And now once, okay, is it too dark now?
No, it's fine.
Okay, no more light. Maybe okay, let's change, you know, I change back. Okay, so now I will give you some other maps of the same type, and they are constructed almost in the same way, but they do not produce this triangle cross a square, but they produce similar shapes. Okay? So similarly.
Can you tell us why there is an embedding in another sense?
Sorry?
Will you tell us an embedding in another sense and in another direction or not?
Ah, very good point. Let's do it. So, well, let's do it. I didn't prepare, but it's a nice question. In some sense, you want to do exactly the same the other way around. So my curved, my colors of before still make sense. So what did we do? Let's repeat. We had something like, I told you where to map. Doesn't work. Maybe we repeat. So this was mapped to this, and then this to this, and then this. Right. Well, here it should be better like this, very narrow, right? So I don't want to. Right. So this was sigma, and the way the map in the other sense is almost the same. I just have to go a bit. Now I want to go into. So if I want to go the other sense, I have to start a little bit too big. So I do the following. I start here from 1A. And I want to go back, something like sigma inverse, but it's maybe not exactly sigma inverse. It's just the other way. And I want to go towards the disk. So, I do almost the same. I start like this, map it here. And you see, now at the end, I must map the full thing. So here I become a bit too big. Actually, you can put this also. You can put it here, just here on the edge. It's more natural. And then I do this. Oops, doesn't work anymore. And at the end, I just need to get everything. And I map it somewhere here. And here it will be A plus epsilon. So, yeah, this was not very nice. I mean, there is an intermediate. Where is it here? Do you understand?
No.
It's almost the same map, but it should be, when here is A, well, it should take everything. So I have to map a bit too much.
Mm-hmm. Yes.
But this will also, and then I have to restrict. So where is this map defined? It's defined on this rectangle 1A, and I take sigma inverse cross sigma inverse. Sigma inverse is not a good name. Let's call it phi. So I take phi cross phi and restrict, and it is defined on here. Rectangle A1. A1. No, it's even a bit more. It's a bit more than the rectangle A1. And a bit more than the rectangle A1. And then I restrict it to the simplex, the triangle cross the 0, 1. And this restriction will go almost into the ball for a similar estimate, by a similar estimate. Do you believe it?
Yes. I do.
Great. Jura doesn't believe it, but I'm used to that.
I don't know.
Well, you cannot write down exactly the same mapping because it was not subjective. Well, it was, but only not in our construction, only after this McDuff limiting argument. You see, what I could have done, I could have used high-tech to prove that with a limiting argument, with epsilon going to 0, I can even arrange my embedding to be a symplectomorphism between the two. In the sense, the limit is still injective, and every point is in the image. Then I not even need to construct the inverse mapping. But this is hard and uses J-curves, and it's not needed here. You can also say...
You are saying you cannot do it with just convex surfaces.
Without J-curves, you cannot do it. Now you can do it with Duchovsky trick, but it
Kind
needs
of
a subtle...
And no exhaustion. Exhaustion would work.
Oh, exhaustion would work, but you have a sequence of mappings that are nested, and then you have to change the vector fields, and then you have to use local flows, and it's a little bit technical. It can be done now without J-curves, thanks to it can be done. It can be done without J-curves, but it's a bit technical to write down, and we do not need it. So what we do it in some detail, the other map is exactly of the same type, just again defined on a bit too big set, and it does the job. And there is an epsilon in business, but we can take infimum and it will go away. Okay. So you find that in my stupid book on page, chapter 3.2, written by Edith Zehnder since he didn't like the geometric argument. Is it okay?
Yes, thank you.
Thank you. Okay, so now I want to do variations of this. So similarly, I do the following map. I take sigma of a bit different form, Jura's beloved diamond, and here so before we decided to map everything to the left, but we could also have decided to map everything to the right, or we could have decided to start from the middle and to go concentrically out. So I now do this concentrically out. We could define sigma in a different way, sigma diamond, and it goes like this. It's maybe nicer. So maybe colors are good. So this one goes to the middle, and this one here, and this one just here. And here is, of course, one line. Well, okay, I shifted it. Now here is maybe, sorry, maybe I don't want to shift it. It's okay. No, let me do it like this. So here is 1/2. It doesn't matter. And the last one maybe like this. So here is a over 2, of course, plus epsilon, and here minus a over 2. Minus epsilon. You understand the map? It's of totally similar kind as before, and it is now going symmetrically out in area. Okay? So let's check what the same product map as before does. What does sigma cross sigma do when we restrict it to, so again, this is the disk of size A, and we restrict it to the ball. And well, it does up to epsilon rounding, it does this. You can guess it. So here, of course, it's always this boring, okay, now it's minus 1/2, minus 1/2. It's maybe, it doesn't matter. Here it's just always the same square. But here it's a diamond. And here is a over 2. Do you believe that? You see, exactly as before, the area condition meant that the constraints become linear. The R squares becomes a linear thing, and by symmetry it must be something like that. Cannot be anything else. You can also restrict the whole construction on the positive parts, check that is this, and then by symmetry you have to put signs. You believe that? Okay, this is an exercise. Now maybe it's good if you try to do that in 3 minutes. It's easy.
Felix,
okay.
Could you please show the right part of the blackboard? The right. Yes, okay. Thank you.
So the key thing is that you can forget about the y coordinates and just remember that a ball is a Lagrangian polygon, namely this one. Okay. So this is now you can kind of play puzzle. You have such pieces, and you know what a ball is. The image ball is this, and smaller balls are different. And now we can already do a part of the table of Kermov. Okay. Okay, so corollary. What? Always confused. Mm-hmm. So in the table, maybe I show you the table again. So we get bigger or equal means that we can realize the answers in the table, right? Well, bigger or equal means that we have found an embedding, and less or equal mean that we construct an obstruction. Well, we have solved this for k less or equal than 6, and for k square. For all square numbers, we also did it. Okay, I'll prove it. So you see, this is a ball of size 1. right? And now you go to the middle. So, for instance, we have found a full packing of a ball by 4 equal balls, right? 1, 2, 3, 4. Well, the blue one we didn't do, but instead of going always to the left, we could also go always to the right. So with left, left, we make this. With right, right, we make this. With left, right, we make this, and so on, right?
Wait. We can just simply rotate, no?
Yeah, rotation is maybe. Or you can do coordinate swap. That's fine. X1, X2 goes to X2, X1. That's right. Permutation. Yeah, that's also good. Yeah. Yeah. Okay. So you see what was in the table. In the table there was a one. So in the table there was written that the percentage of a ball you can fill by 2 balls is 1/2. You see, 1. It means 2 of these 4 fill 1/2. So this 1/2 in Gromov's theorem is realized. That you cannot do better has to be improved. And of course, there was for 3 balls in the table, well, there was a 3/4 that you can only fill 75%. Yeah, true. Take any of these 3, any 3 of these 4. Of course, you have to show you cannot do better. But the Gromov 1 in 4 we have realized because we have constructed a full packing by 4 balls, right? Fine, Alexei?
This is a picture on the plane. So this means that just you take a 2 disc and so this is this picture for the projection on the triangle component.
Exactly. This is for now on. Yeah. So this is Q1, Q2, because the P guys, they're always squares 1, 1, 0, 1, 0, 1, or -1. You can translate. The Y I just forget now.
Mm-hmm.
I can, because of a ball, I think of a polygon cross a 1 square.
Mm-hmm.
Right? So the Y I do not picture anymore.
Mm-hmm.
You can try dimension 6, then you have to play with 3 simplices somehow, but it will not be sharp. Okay, so this proves this. And this is similar, right? For 9 and for 24, you can do this picture. And you can take it's not beautiful. Shit. What? No, you see, you understand that instead of, okay, let's do it. You know what I mean? So 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Know what I mean? But you see, this is a bit stupid. It can be much easierly done. It can also be done like this. You can also subdivide here and put the squares here and make them smaller. You see, a mapping times 10 in the x and divide by 10 in the y is symplectic. So you can also put the stuff here. This is easier. So this is actually trivial. This is, once you know that a ball is a triangle across a square, this is trivial. You just divide here and scale back, right? Okay, good. But now I want to do 5 and 6. This is more interesting. And you can do it this way. So I give you a 1 ball. 1. And now, well, I have to go to you have to do 5 parts. Okay, 1, 2, 3, 4. 1. 5 parts. Here is 3 and here is 1. Okay, 1, 2, 3. Shit. Oh, let's do it. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Not so nice, should be okay anyway. And okay, so here is one, here is another one. It should be size 2/5. Here is another one. Here is another one. So this is 2/5. And here are 2 other ones. And they are diamonds. So you see the diamonds, they are all of size 2/5. And they realize for 5 and for 6 balls, they realize the number in the Gromov table. You have to, compute the percentage, but it's easy. Okay, so now this is okay. Okay, and to do it for 7 and 8 is known, but it needs really tricky. It needs tricky considerations and one more technique, and you can find it in the bigger text. So if you like to see, you can go to the bigger text and check for 7 and 8. Maybe I just write it for k equal to 7 and 8. It needs a bit more, and you need one more trick. You need tunneling. And you can see it on page 1114 of the FAT text that Alexei sends you. I'm exhausted. Well, 104 minutes, man.
Great.
Okay.
Thank you.
Okay, Felix, thank you very much. So are there some questions?
Yeah, good point.
I wanted to ask something.
Yes.
It's a toric domain of this shape, but this is really not, this is an explicit but non-trivial curve. And what I mean is, over this point, you should take a circle, over this point, a torus, and over this point, a point. It's a toric picture, but it's very much related of what we did.
Yeah, I see.
So how you split coordinates is really crucial. You cannot just say the shape, you have to say which coordinates you have.
Seminar, you have another link. For the seminar, you should use another link. Then send in my message. Yes.
Okay, I'll change it. Yeah, I understand. I will go.
Okay,
Great.
thank you so much. Bye.
Ciao. Thanks for watching. Bye.